Yo, hi guys, this is Kai. So right now I'll be giving you guys like a mathematical foundation or like an introduction in general to optimization as a whole. Because in the end, like for example, nowadays AI and ML is quite popular, right? Like for example, people might say, oh, I'm doing like the optimizing the weights of a linear regression, which is the simplest supervised learning model. Or maybe I can say, oh, I'm doing gradient descent, or I'm doing hyperparameter tuning, yada yada yada, logistic regression, whatever. There's a lot of ways that we can do optimization, and honestly, they're all optimization. So I'm just wondering, and also you might be wondering as well, also because of that, it's just AI and ML. So optimization, is it just AI and ML? The answer is no. But our optimization generally is just an applied math problem. And frankly speaking, that is something that people keep misunderstanding. And because of that, right now I'll be sharing a bit on the actual foundation or the actual math behind it, such that you can actually see, actually it's just math. And the goal is universal across all different types of optimization. So once your understanding for this is clear, it should be quite generalizable towards other AI and ML stuff as well. But what makes this a bit unique is this specific optimization that I chose is unique is these two things. So higher order and binary. So what do they mean? So higher order essentially, this actually comes from the idea of statistics. So essentially in statistics there's this thing called um, moments. Moments. So for example, the first moment in this case is x to the power of 1. This is actually mean. Second moment, or expected value by the way. Second moment will be variance. Third moment will be skewness, and fourth moment will be kurtosis. But as you can see, generally it is the uptrend towards 1, 2, 3, and 4. So fourth moment, power of 4, kurtosis. And if you look at the actual formula behind them, each of the four formulas is just changing the power within the formulas, right? Everything is the same. But where does the order idea come from? The order idea actually came from this in the sense that the full term for order means order of correlation. The reason why it's called order of correlation is because essentially, like for example, x squared, right? We can actually represent it as like two x's. And in this case, we can think of it as a covariance really, right? It's a covariance matrix, or rather, we are modeling the interactions between the variance of two variables. Then what about this? Then what about power of two? Third moment, right? So this co-skewness and this co-kurtosis. So this is where the idea of order of correlation came from, where we are trying to model the interactions between two or more variables. So that is for high order. For binary, essentially it's just, you can think of it as 0 or 1, right? Say x can be 0 or 1. And in the business sense, you can think of 0 as not making a decision and 1 as making a decision. So that's why for our optimization model, say if we have a function here, right? Ax plus ab, x to 1. Essentially, what we are trying to do is that we are deciding whether we should include the a here and b here within the coefficients as the output of this function. Because in this case, if x1 equals to 1, x2 equals to 1, then the objective function or the function itself will actually be equal to a plus b. And how the computer solves this problem is actually based on, or how the solver actually decides on whether 1 or 0 is entirely based on the goal of our optimization itself, which is whether we want to maximize it or minimize it. In this case, because say if like A and B are both 1000, right? and we want to maximize the objective function. This is called objective function. Then essentially what we need to do is what the solver will automatically choose is to maximize A and B, choose 1 times A times 1 plus B times 1. And because of that, our overall objective function will be 2000. Now, of course, here's the issue, right? Generally, solvers, they are not binary encoded, meaning that when they actually give an output, it can range from negative infinity to infinity. Meaning that, like for example over here, if our goal is to maximize the objective function here, then my x1 and x2 will just be infinite. Like that, I'll just solve the problem just like that. Everything is infinite. So because of that, actually later on I'll actually show you guys on how we force the solver to only output 0 or 1 as the decision variable, which is something called constraints. So it's essentially rules in which we try to force the solver to doing certain things within the boundary of the rules. And the way that we do is actually something called penalty. Like the way that we actually implement the constraints called penalty. I will share it with you later. So, all right. So best way of like talking about optimization is maybe like a real world example. Say, like for example, if you have a friend called Isaac, he's going SAP, and he's going to a department where he often meet Fortune 500 company clients, where they'll ask him, "Hey, okay, I'll have so many suppliers, products, and carriers. Which one should I choose? I want it to be cheap, fast, and reliable." So okay, you're Isaac, right? So you're smart. So what you'll do is that, based on the data set, what do we have? Okay, so cheap means my manufacturing cost from my supplier must be low, right? Or maybe the product cost might be low. Who knows? Fast. Oh, maybe this will be lead time. In a supply chain, definition of lead time is essentially when the product is first created and shipped to the consumer. So generally, the lower the lead time, the better. Reliable is, in this case, it is defect rates. So whether your product has defects, and what is the percentage of it out of the total amount of products you have. So say, like for example, in the case of automotive industry, generally the higher the defect rate, the higher the lead time as well, because you need to redo your entire supply chain, or part of the supply chain, such that you can like fix the machinery, make sure that refactor the entire car and stuff like that, which can take quite a while. And you need to recall some of the cars back for safety concerns as well. So generally, um, that's what we call by defect rates, and it's actually very important in supply chains. And in our case, our objective function is to make it such that our score is as low as possible. So the function here has to be as low as possible. So maybe the best result would be negative infinity. But of course, cannot be, right. So because of that, like for example, in this case, right, if I want to save costs as a client of Isaac's, then Isaac can just say, "Oh, then just don't do anything. Just ignore, just stop with this stupid idea of like manufacturing stuff. Just don't do anything." And that saves costs. So it doesn't make sense. So because of that, we really need rules in order to satisfy or fulfill the actual business need. And in this case, is to make decisions on which are the best suppliers, the products, and the carriers that maybe the manufacturing firm should pursue. So this is our idea that we are trying to pursue. Okay, so now I need to share more on the notations and the units, which can be quite complicated. But generally, this is the objective function. Okay, so IJK is essentially it is a Excel sheet, right? And our columns here are all of our features, and each of the rows here below it are just observations. So just think of IJK as like if I equals to 1, that is the first observation. j equals to 2, then is the second observation, j equals to 3, then is the third observation. It's just that meaning. This is the decision variable, which is the x and y here. Now, next is the coefficient. So the coefficient, generally, it can be decided in two ways. Number one is I fix it. So by fixing it, it means maybe I can just do 0 or 0.5 or 1. But instead, in this case, what we are doing is that another type of coefficient fixing. Because our coefficient actually has to be constant. The way that we actually get the constants for the coefficient is that, by the way, this is a coefficient. It's actually by getting, from the data itself, data set itself. Like for example, in this case, average supplier cost, right? Manufacturing cost, shipping cost. Based on a specific supplier, like supplier A, I'll just average out all of the supplier costs. Manufacturing costs, a specific product, I average it out. And all of those will be our coefficient here. As for the past year, these are also coefficients. I'll share more later. I'll share everything later. Okay, so order, just now I talked about the moments, how it relates to moments. It's actually order of correlation. And generally, the reason why we are exploring this in the first place is because right now, classical computers can only do second order optimization max, which is this. But the issue, right, is that in the real world, most things have more than two decisions needed. That like if something happens, there's probably more than two reasons why it happens, right? So because of that, we generally need to have three or more in the real world, like features in order to actually model what is the causal inference of the final output. So for now, only quantum is able to solve third to fifth to seventh order optimization. Like for example, directory from QCI, this company called QCI. They are 150 mil bill publicly listed company. You guys can have a look. So yeah, but of course, generally for classical, I understand that it can only solve up to second order. But technically speaking, we can introduce an auxiliary variable, right? For example, for the x2 and x3 here, and just replace them with x. Then my x equals to x2, x3. Then right now I'm just solving, my solver is just solving x1 times t, right? As an auxiliary variable. So if that's the case, I do like x to the power of 1000. I just introduce everything as two like auxiliary, into like an auxiliary variable. Then maybe this entire thing I take into t, right? Then it's a first order problem. Then technically classical solvers can solve, right? But actually the thing is that for this entire process, it's very, very complex. And the reason why is because when we are doing this, at the back end, essentially we need to make sure that t actually matches to x to the power x2 and x3. And for solvers, right, they don't know. Like for example, say at the right hand side it can be 0. But on the left hand side on t it can be a 1. It is actually quite annoying to deal with. But I'll share with you on how do we deal with this issue, which is actually what we call Engadget. Quite cool, like gadget. It's like your spy. Oh, never mind. Okay, anyways, I'll be sharing it later. Essentially, we are introducing a penalty to the equation itself, such that it punishes um the solver whenever this left hand side and right hand side does not match. Can? Alright, so am I recording? Okay, good. Okay, so now Cubo and Cubo. So this is the exact math behind it. As you can see here, there's like x to the power 3. And yeah, I think that's what I really shared. Okay. Alright, so now on and off switch. Now we are talking about binaries. So like I mentioned just now, each decision variable can only be 0 or 1. So what this means is that across the entire data set, say I have like a supplier B, A, B, and C, you know, if I'm a solver, right, sometimes I might be tempted to just say, oh, I don't want to choose any of them. 0, 0, 0. So the sum of all of them is 0. This will be 0. On the other hand, like for example, if I want to maximize the objective function, then I'll choose everything 1, 1, 1. Then this will become 3. So essentially, the math behind it is just, all of the different types of categories of suppliers, how do we make sure that we only pick one? This is what I mentioned about earlier. We actually need to introduce penalty terms to force this. And it's something called one hot penalty. You can think of it as one hot encoding from ML or data science. But in this case, it's different. Just think of it as forcing each decisions to be only 0 or 1. Okay. I'll share about the math later. Singlets, pairs, triplets, penalties. I think I explained this already. Okay. So next I'll be talking about first order, which is linear programming. So for first order, essentially what we are doing is that in this specific business case that Isaac is doing, all of the suppliers here, here's an example by the way, all of the suppliers here, what we're trying to do in terms of finding, in terms of the objective function itself, is that we are trying to pick one category each, like A and B. Then we are going to sum their costs separately, and then we will get their mean. So in this case, supplier A has 4, and B is 4.6. And the reason why we do this in the first place, because again, our objective function is this, right? So this will be the coefficient. That's why earlier I mentioned that in this case, we are doing data-driven coefficients, where everything comes from, like in this case, it will be the mean of the supplier cost based on their unique category. And over here, BP, right, manufacturing costs, we're summing this and this, getting the average. Then over here, we are getting the average of 5.5 and 5.6. Shipping costs, we are, for the carriers, we are averaging out the X and Y separately. Then boom, after we do all of that, essentially what the solver will do is that it will test all of the different combinations of each of the suppliers and products and carriers, such that in this case, we are trying to find the lowest score as much as possible. And in this specific math example, we are choosing uh supplier A, product P, and carrier X. So then essentially it's just the average of these three, or the sum of these three numbers. But on a glance, this is not actually the minimal value, right? Because for the product, instead of choosing P, you can choose Q instead. And as you can see, Q is actually lower than P. So because of that, actually, we can change this to 5.55, and the solver will do it automatically, and it will give you a number that is actually the real global minimum. So yeah, that's how we do linear programming. It's actually quite easy for the solvers to do. Okay, so now let's talk about pairs. So second order optimization. So for this, it will get a bit more complex. In this case, what I'm doing is that okay. So before that, we relax a bit first, and I will introduce you like what baselines are. So generally, in terms of baselines, what we're trying to do is that first of all, we are summing up all of the different costs, like for example, in this case, supplier costs, and then we will get their average. And the reason why is because we want to get the global average of a specific um, feature. Like in this case, it will be supplier costs. So supplier costs and average it out. there will be lead time, defect rate, and manufacturing costs as well over here. And the reason why we need the baselines is because in our equation that I'll be showing later, right? Essentially, when we decide on a coefficient, or rather to solve our objective function, which is to get the minimum score, we need to make sure that the A here is smaller than the baseline. Because if A is bigger than the baseline, then this will be positive. This entire thing will be positive, which is bad for our minimalization objective function. On the other hand, if our coefficient here is smaller than the baseline, then it will be favorable. And because of that, we need some way to introduce a baseline. And in this case, it will be the global average for each of the features. And this is the exact math behind it. It's a bit overwhelming, so bear with me here. So this over here, LT, which means lead time, DR means defect rates. We are just getting the coefficient, which is the A here. And for the global, it's the baseline that we have. What the hell is a W? It's just weights. As you can see here. I'll share more about it later. But first of all, let's deal with what we have here first. So just an example for us to have a look behind the math on it. Global minimum, we get all of the averages. For the AP, like for example, for our coefficient, what we'll do is that we will essentially do unique ordering of supplier and product. Meaning, like for example, in this case, we have AP, right? Unique, they are unique. So we'll be getting their specific lead time and average it out, and also their defect rate. On the other hand, say if I want to do for, and if this is AP, right? Then I will also do it for EP. Then AQ is unique versus all of them. So I'll just do AQ as well. So the solver will help you to do all of this math. Actually quite rapidly here. So essentially after we get the coefficient from the averaging out from the unique categories, we will apply this math formula here such that we are able to get a new coefficient, which is a coefficient that combines both two features, so x1 and x2, the properties of the data from two features. And in this case, it is over here, this is the lead time, and over here is the defect rate. The reason why we need to create a new coefficient is such that we are able to model each unique pairs of categories as much as possible. Because like for example, if x1 and x2, right? If I have an x1 and x3, or like x2 and x3, all of them will have their own unique coefficients. And the coefficients here, because it's data driven, right? It will be affected by the specific decision variables here that we chose, or the which is x1, x2, x1, this one here. So because of that, we need some way to have a coefficient that dependent or have a relationship with both of them. In this case, it is a math formula. Now, as you can see, there's an extra 1 and 50 here, right? So here, this is actually the W1 and this is the WDR from earlier. WLT, sorry. WLT and WDR. So why did we choose 1 and 50 in the first place? This is where optimization gets tough, and the reason why that for me optimization is more of like a business requirement thing plus applied math. Quite some advanced math. The reason why is because, like for example, the 50 here is actually not chosen by default. Like for example, in the case here, like how do you actually create the weights? So in this case, say, for example, you want to model and say, hey, if I want to model every time there's a 0.01 increase, which is around 1% increase in defect rates, then this will translate in maybe 50 days of lead time, which is quite bad actually. But this is common in automotive. But essentially, the math behind it is just 50 divided by, let me get my calculator. Ui, 50 divided by, yeah, carry my math has issues. It's actually this one. So over here, 50 times 0.01. Okay. Yeah, correct. It means that generally, oh, sorry. Oh, sorry. So every time that but for this specific formula, it's actually my bad. So is d equals to 0.5. This is equivalent to saying that for every 1% increase in defect rates, it results in a 0.5 day increase in lead time. Uh, so all of these requires quite strong of a domain knowledge. Yeah, so that's why generally, for example, in finance, portfolio optimization, generally you need to have very strong finance background in order to do that in the first place. So, as well. So this is something that quite a lot of mathematicians cannot do. Anyways, this is the idea behind tuning the weights. Everything is based on business needs and real world empirical data that you get from the real world. Okay, now let's talk about third order. So for third order, which is triple effects, what we'll be doing is quite similar to what we did just now. The only difference is that for the coefficient that we have here, we have more things to consider. Like for example over here, right, this is what we have from the previous formula here for a pair. It's actually the exact same. But what we'll be doing more in this case is that we are introducing more weights and also the third variable here for us to compute the coefficient. So again, the question that gets back again is how do we decide on the weights again? So in this case, what we're doing is that our weights over here for the lead time is much higher than the rest. 0.8 versus 0.2 versus 0.5. And the reason why is such that we want as a business requirement for the lead time to be prioritized under the objective function. Meaning, if my lead time here is too high, which means that this is positive, then my objective function will be severely penalized by having a higher value as compared to the rest here. So, for example, let's just say that per unit of increase within the lead time versus per unit of increase for the defect rate, right? This will be penalized more because of 0.8 for the coefficient. But to build on top of that, this also means that if my lead time is really low, my objective function will really reward it as well, reward it quite significantly as compared to the rest as well. So it's sort of like a trade-off that you have that is good. But as a whole, what the idea behind the weight is just for us to prioritize specific decision variables or the features that we have here. Okay, so now let's show the math. The math over here is essentially what we have in this formula, just on numeric format. And yeah, what we're doing is that we are getting, for example, lead time, right? We are getting these three. So these three unique categories. And APX, APX, this as well. But for example, if we want the lead time of AQY, then it will be written as this. Ta-da! And over here, as you can see, the alpha, beta, and I think it's theta. This is theta. Or nu, I forgot. Or rho. But anyways, over here, here are the weights that we have here that we fixed earlier to reward or punish specific teachers as much as possible based on our business needs. Okay, so I think you're getting the gist here already. Now we need to put everything back together. So over here, as you can see, x1, y1, this is just linear form, linear programming. And in this case, this is first order. Next, this is second order because there's 3 decision variables. This is third order because there's 3 decision variables. The coefficients here are decided based on what we showed earlier, which is for a single pair here is just normal averages. For the cube second order, it will be what we did here as well. This is the other formula that we have that we had an issue with in terms of trying to determine what should be its weights. And over here, this is the coefficient for the third order, the 3 variables, which is what we just did. So as you can see, all of this is just math. It's really just applied math. This is not ML, this is not AI, this is just math. So because of that, it's quite doable. But this also means that if you want to introduce constraints, right, it means that we have to add on something extra, like a P penalty. Legit is just add, just a plus, such that it follows a specific constraint. Because there's no like magic behind it, it's legit we just add on to it to force it to not to get the ideal score that we want, to minimize the score such that within the boundaries of the rules. And in this case, the rules are quite obvious, right? But generally, there are 2 main rules related to this. Just now, I talked about one-hot encoding. So this is the one-hot encoding math. As you can see, there's this squiggly thing. You can just ignore. It's not as deep. It's not that deep. Over here, this is the exam math behind it. So as you can see over here, so what this means is that out of all of the suppliers, A and B, say A and B, if we just pick one of them, then it won't be punished. There won't be any penalty. But if we pick both of them, or we don't pick any of them, we will introduce a 100 penalty. So meaning the objective function is just plus 100. And it won't be the minimum score as a result really. Hence the solver will not think of this as the best ideal option. Think of this as the ideal option. So we are using this to get what we don't want. We are using this to get what we want as a whole, which is to force just one decision across all of the suppliers. Next is on Engadget. This is the issue that we have here just now, which is I can just anyhow encode x to the power of 1000 to t, right? Which is tough because t might not be equals to each of the variables here. Like for example, if one of the variables here equals to 0, sometimes t can be equals to 1 as well. So we must force the solver to use his brains. Or we make the left hand side and right hand side to match. So in this case, what we are doing, or this entire thing, what we're doing is that we are, like for example, the supplier A and Z, right? So in this case, no, sorry. Ignore what I just said. So t equals to y and z, right, in this case. So if y and z is 0, this should be 0. But if this is not 0 and this is 1, then we introduce a penalty here, which is 3. And as you can see over here, the penalty will be 200. If say 1 times 0 is 0, but the t is equals to 1, or the other way around, which is this, then we will penalize it by adding 200. And if both of them are 0 and t equals to 1, they will add 600. How do we decide the penalties? Generally, it's the same. It doesn't really matter as long as your penalty is high enough so that you can punish the solver as much as possible. This is what I mentioned about how it works. but we actually need this entire thing such that we are able to convert a Hilbert formulation into a Hilbert formulation such that a classical computer can solve. Okay, so this is the linear algebra behind it. I won't go into details here, but I think we may need to go do more research on this because we need the linear algebra math behind it such that we are able to solve the problems much faster due to the amount of decisions that we need to consider to get the lowest score to reach the objective function here, which is to minimize the score. Now the question is, how do we choose the penalty? Like the one that I mentioned here, 200, 200, 600. How do we actually choose it? Honestly speaking, again, I say it's subjective, but I'm guessing, but like rule of thumb is based on the maximum value that we have from the objective function, just times 2 the penalty. So that one just times 2, then just make it equal to the penalty or higher than the penalty. Lower than the penalty. So the penalty has to be higher than the maximum objective function without it. So I think that's it. Yeah, but when we actually implement it, we just anyhow put one. But this will work. This is the word bound. Okay, now to summarize. Say we have two candidates here. We have three features. Now, what does cubic or our Hilbert optimization do in this case? Now, once we make our decisions, we choose one supplier, one carrier, one whatever, and we get their interactions, the best interactions out there between two pairs, and over here is the interaction between three variables. And we make sure that the penalties are satisfied. As you can see, it's actually a plus. That's why I said just now that penalties are, we need to add them in as a plus operator. And once we sum all of them up, that will be the score. And the goal of a solver or optimization is such that we are able to get a score that is as low as possible. So we will need to explore quite a lot of candidates in general in real-world datasets, maybe millions of rows. But in this case, we are just choosing between two candidates here. So yeah, that's about it for higher order optimization. If you have any questions, can always ask me, text me. But yeah, I think that's about it really. Thank you so much for today.